Okay, so our first topic tonight, we have a double hitter tonight. It's entitled Best Practices Using Heat Pumps. And it's our favorite topic, it seems. But it's heat pumps in energy efficient buildings. It's by Bill Amann, who's president of his engineering company called M&E Engineers. I saw Bill's talk first in February, this last February, for a New Jersey DEP, Department of Environmental Protection meeting on best practices to create energy efficient buildings. Bill is the best man for that topic. And so we're very privileged tonight that Bill agreed to present his material on the basics of heat pumps and then talk about the relative efficiencies and criteria to select possible heat pump system designs. That's going to get into much more detailed. Everybody really has a unique situation in their house, so it's like that. And then he also agreed to discuss the most recent energy efficiency code, which is really important to us. One of our 50 by 30 team members' team goals is to influence the building code in New Jersey. And Bill has a special agitation, and that's about how do you inefficiency in policing the compliance to increasingly tighter energy efficiency standards. So Bill, I just told you a little secret here, sorry. But with that, I'll let Bill lead off, the first speaker of tonight.
Thank you very much, Steve and Pat. Pleasure to be here. I didn't redo the slides. I'm just representing the slides from the February presentation I did in February, but I've given a longer version of this. This is a 90-minute presentation on heat pumps compressed into 30 minutes. So I'm going to try to move pretty quick and try to squeeze the code and compliance issues in at the end. So I'm going to move quick, and we're going to hold the questions to the end. So I hope I don't lose you, but I want to make valuable use of your time. So I know a lot of the sessions that Steve and Pat have presented have talked about heat pumps, and a lot of people sort of understand them, but don't necessarily understand all the, exactly how they work. So I want to give some of the fundamentals on just how heat pumps work, and then air source heat pumps, which are now over the past 5 to 10 years, we have these cold climate heat pumps. What's the difference between those and water source heat pumps? And then there are all the variations of water source heat pumps. So ground source heat pumps or geothermal heat pumps are water source heat pumps. They can be closed loop or open loop. And then I'll touch very quickly on outside air ventilation for buildings that are kind of related to this. So can't talk about any of this without reiterating the main point of energy efficiency or electrification is to minimize the energy use, right? The less energy we use, the smaller the problem becomes, the easier the solutions come to hand. And it will always and forever be true that the cheapest, the cleanest, the best kilowatt is the kilowatt that you never use. There's universal agreement on that. So there's lots of things that go into energy efficiency, Energy Star appliances, sealing the house, applying energy management, high efficiency water heaters, lighting, etc. is all part of this. So the goals to get to decarbonization, the first thing we need to do is minimize the energy use, and then go to electrification, because we can decarbonize that. We cannot decarbonize natural gas or oil. And then as we do this, we have to remember to maintain our indoor air quality. 1979, when I first got into this, yes, I'm dating myself. We had the energy crisis. and we tightened up buildings and we created sick building syndrome because we weren't doing it the right way. So we know better now. So let's get into heat pump operations. Heat pumps, people say it's not a good name. I think it's a great name because you're pumping heat from one place to another. That's how they work. An air conditioner pumps heat from inside your house, from inside your house to outside your house when it's in air conditioning mode. When it goes into heat pump mode, it simply works in reverse to pump the heat in the opposite direction. Heat pumps follow the first law of thermodynamics. Energy can neither be created nor destroyed. So they don't make energy, they just move it around. They pump it from one place to another. And we can measure the rate of efficiency, if you will, or the coefficient of performance is the ratio of the useful heat movement that you get into or out of a given place divided by the unit of energy that you put into it. That's the coefficient of performance, and we will show you how the coefficient of performance is related to the various things that get into determining the coefficient of performance. This is what a system looks like. Inside your house, you have a coil, and outside your house, you have a coil, and there's a compressor in between. And it pumps the refrigerant from one coil to the other. Typically, as an air conditioner, the indoor coil is called your evaporator. It's cooling the air. The refrigerant absorbs that heat, gets pumped to the outside coil where it rejects the heat. By taking the same system and inserting a reversing valve, we just reverse that process. So there's nothing magical about this. Getting ahead of my slides here. The coefficient of performance is directly related to the thermal lift, or the Carnot efficiency. All refrigeration cycles basically use this Carnot cycle. It's a reversible isothermal gas process that was first proposed in 1824. It's been around quite a while. So depending on the temperature difference from where you're pumping from to determines the maximum efficiency. In the wintertime, in a typical house, if it's 30 degrees outside and 70 degrees inside, we've got a 40-degree delta. We've got 40 degrees of lift. In the summer, we're trying to maintain 75 degrees in the house, and we're rejecting it to a 95-degree outdoor ambient, we've got a 20-degree delta. So the system is going to perform differently, have different efficiency or COP in the winter and summer. And because engineers are strange animals, we don't use the same term. We use energy efficiency ratio for cooling. We use coefficient of performance for heating. Now, this is what I'm talking about here are called air-side heat pumps. And the old style ones that have been around for a long time only work down to about 35 degrees outside. After that, they kind of quit. They weren't designed to operate below that. And what they would do then at below 35 degrees, they would start going into conventional electric heat, resistance heat. Resistance heat has a COP of 1. You put 1 unit of electricity in, you get 1 equivalent unit out. So not terribly efficient. And since electricity is kind of expensive, when these resistance heaters are cranking in December and January and February, people are getting whacked with really large electric bills. So they developed kind of a bad reputation. But to the rescue, we now have cold climate heat pumps. Cold climate heat pumps have been around since 2007. Mitsubishi introduced their first hyperheat system. And I have some of their systems at a cabin up in the Catskills. It still has 100% of its capacity at 5 degrees outside, and it still works. It's not at full capacity, but down at negative 13. Actually, that's on the slide here. So these are called, the acronym is CCASHP for cold climate heat pumps. They employ variable speed, variable flow refrigerant. And as I said, they maintain 100% heat capacity down to 5 degrees and operation down to minus 13. There's a great resource if you want to go looking for a unit. The database of available systems from NEP, which is the Northeast Energy Efficiency Partnership. It's almost an overwhelming amount of data and information, so it is a little hard to get through, but they are qualifying every unit from every manufacturer out there, which would include Daikin, LG, Fujitsu, Sanyo. Their American manufacturers are just starting to bring their versions to market. There really aren't any available yet that I know of from America. I think Goodman might have some, but otherwise not from American manufacturers. What do they look like? Well, this is 2 of the units at my cabin up in the Catskills. So, you know, you see these sorts of outdoor units outside of buildings all over the place. They're not super attractive, but they're not super ugly either. It's just something you have to put up with. And then the indoor units. This gets a little confusing because they really started off with these wall-mounted units that, if you're familiar with mini splits or ductless units, they do come in that version. However, they also come in all these other versions. You can get vertical air handlers, concealed ducted air handlers, floor standing units, ceiling cassettes. So they come in all sorts of configurations to suit, you know, the house, and we do use these in commercial buildings as well. There are, in fact, large variety, larger sizes of these units too, that we've used in schools and other places. So let's get into some of the performance information here. So typical cold climate air source heat pump, the energy efficiency ratio is about 15. So a conventional air conditioner is probably going to be around between 10 and 12. These are more efficient at a rating of 15. And then more importantly is the seasonal energy efficiency ratio gets as high as 23. That takes into account the fact that they perform even better under part load conditions. The EER is at full load nominal ratings. The seasonal EER takes into account your part load ratings. Now in heating, the standard rating temperature is at 47 degrees, and at 47, these units will give you a coefficient of 4. So for every 1 kilowatt of energy that the unit uses, you get 4 units of energy into your house. So the price of that kilowatt, if it's 16 cents a kilowatt, well, now you're only paying for one of those, 1/4 of that. So you're only paying 4 cents a kilowatt, essentially, to heat your house. You can look at this data on NEP of the heating seasonal performance factor. Again, this gets into the part load performance, and depends on where you are. Again, it depends on the outside temperature. So southern Jersey is zone 4 in the ASHRAE climate zones. North Jersey is climate zone 5. So these are some of the typical values. So water to air heat pumps operate the same way, except that they use energy from a fluid instead of the outside air. And that's just a diagram of the refrigeration system, but all the components are the same, except that outdoor unit, instead of being a coil, is a water to water heat exchanger. This is the same system, again, just reverse the refrigerant, and you get it into the heating cycle. And these come, again, these are typically more for commercial applications, but I've put these I put one of these in a passive house home. We've done small buildings. We've done some for Audubon, for some of their buildings with this type of unit. And in and of itself, these are pretty efficient. But that water has to get connected to something. So you don't have an infinite supply of water at 70 degrees to supply these units. So what do you connect them to? Well, and they come in different configurations, but you'd typically, in a commercial application, you'd have a series of these units in different configurations, but they would be connected to a boiler to keep the loop temperature up in the winter, and a cooling tower to reject the heat in the winter. Here's a diagram of how that works. So the loop temperature has to be kept between a reasonable range of temperatures from summer to winter. So the boiler may come on in the winter. The cooling tower would typically operate in the summer. We've done some buildings where they've got interior zones that only need cooling, and we've used this system to provide heat recovery, meaning that the interior zone units are in cooling mode. They're putting their heat into the loop. The units at the perimeter of the building are in heating mode. They're absorbing heat out of the loop, so the boiler stays off. The cooling tower stays off. And the most efficient equipment in the world is equipment that's off. So that's how you get to try to get very high efficiencies, particularly in larger buildings. So let's look at the performance of these. So in cooling mode, we've now got an EER of between 15 to 18. So a step up a little bit better than the air cool. And in heating mode, our COP's gone from 4 to somewhere between 5 and 6. These are the typical train units. That's using the boiler and cooling tower in a water. It's called a water-cooled condenser water system. Now, take that same exact system, and instead of having a boiler and cooling tower, you're connected to a lot of pipes in the ground. You now have a geothermal system. The same system we talked about, same units we talked about, but they now operate at the loop temperature is slightly different. And there are hybrids where we might use loops plus a small boiler or a small cooling tower. But this uses the relatively constant temperature of the earth to do the work that the boiler and cooling tower were doing otherwise. So this is just a water source heat pump with the ground stabilizing the temperature. Here's a diagram of the loops in the ground. It's high density polyethylene piping. In New Jersey, we typically run 300 to 500 foot boreholes. And the mean temperature of the earth, once you get below 3 feet, is around 55 degrees. We do have to be careful that if you if you run the loop in one mode, if you run it in cooling mode, like a data center all the time, and you will eventually cool the earth off, and your loop temperature will well, I'm sorry, if you're in cooling mode, you're heating the earth up, and the loop temperature will get too hot. Conversely, if you're pulling heat out, it could get too cold. So we very often put glycol in these systems because we'll run the loop down to 32 degrees. Normal temperatures, we talked about the Carnot lift. So if we've got the ground at 55 degrees, moving that to a 70-degree indoor space, you see that's a very small lift. And the same in the summer. Pulling it from 75 down to 55 is a very small lift. So the performance now we're up in the EER of between 18 to 22. And the COP drops to 4 because the loop temperature will tend to drop off in the winter. And like I said, we typically put glycol or brine in that. Now, there's another version. That's an open loop geothermal. So if you've particularly out in an area where you've got you don't have city water, you're using a well for your drinking water. We did this for the Musconetcong River Resource Center. We just take some of that tap water, if you will, run it through those heat pumps, and put it down back into the aquifer through another well. And this is one of my favorite systems. If the water quality is okay, and you use the right type of heat exchanger, this is by far a much more efficient system because that groundwater really does not change temperature. It does depend on hydrology. We drilled to do a similar, like a hybrid version of this in New Brunswick, and we got no water. There were wells all around us that had plenty of water. We got no water. So it's as tricky as well drilling has ever been. But if you've got water, and this is the diagram illustration of the wells, and you typically need 2 return wells for each supply well because you're pumping out under pressure, you're returning by gravity. But if you've got the water, our EERs are now up in the 25 to 33 range, and our COP is up to 5. So fantastic system if you've got the right location, if you've got the well. And of course, the costs of each of these will vary. The air source heat pumps are the least expensive, and that's why they're a great solution. The geothermal, either whether closed loop or open loop, are going to cost you more, but these are all great versions of the same type of system. Let me try to wrap up here. As I said before, when one of the keys to this is really having a tight thermal envelope and a well-sealed house so that you don't need a gigantic heat pump. And many times, especially in a retrofit situation, the house really has to be sealed in order for a heat pump to work, because the old furnace didn't care if the house leaked because it was so, it had so many BTUs that it didn't matter. Well, for these units, it does matter. So if you tighten the house up, you don't want to trap all the pollutants in the house. So you want to pump fresh air into the house. This is a passive house requirement. And basically what you do is you take fresh air from the outside, you run it through a heat exchanger before you pump it into the house. And then you exhaust air from bathrooms and kitchens, run it through the other side of the heat exchanger and exhaust it. And the air from inside the house kind of preconditions the outside air. so that you're not heating or cooling it from scratch. Very, very important for to maintain indoor health. That's a reiteration. This is a dedicated outside air system. It's if you need to cool or heat that outside air, there are systems that do that. And this is just a picture of a building we partners of ours built in Amsterdam. This is a pretty serious office building here. It is a NetZero building. And in Amsterdam, the Dutch are pretty smart about their water levels. They actually store energy from the heat pumps that do this building. They'll store hot water in the summertime at one level of the aquifer, and then use that in the wintertime to improve their energy efficiencies, even beyond what you could normally do. And people at Stockton are work on this stuff quite a bit right here in New Jersey. This is a NetZero energy building, and was at the time the greenest office building in the world. Okay, time for questions. And I'm
Hey, there are so
sort of
many
on time.
questions. I don't. We said we would take 5 minutes after Bill's, so we're not going to get through all those questions, but then we'll circle back around and finish whatever questions we can't get to.
Okay.
And I'm going to skip the first couple of questions because they were answered in the chat. And that is that I think Steve gave some references that someone asked about, and he's also going to be sending out the slides and the recording tomorrow, so you'll be able to go back over it. The next question is, this is from Hank. I moved into a modular house that I'd built and installed 4 years ago. How can I determine when I'm ready to replace the system that came with the house? I wasn't offered the opportunity for a heat pump at the time. So what do you do with a 4-year-old heating system?
That's a tough one. It depends on, well, what is the energy costing you, and is this an economic decision or is it a moral decision? I'm trying to electrify my life because of my grandchildren. So I don't do it for the economics. I want to tell my grandchildren that I've done everything I could. So it depends on what you've got, how efficient it is. If you want to, Hank, shoot me an email and give me some more information, and I'll try to steer you.
Okay, thanks, Bill. The next one is from Holly. She says, I have an old house, 1924, with radiators and no AC. I will have to get rid of, or will I have to get rid of the radiators and install air conditioning pipes?
Yeah, unfortunately, there is no solution for steam or even hot water radiation. But the good news is with those air source heat pumps, you can use multiple of those indoor units. You can create zoning that, I don't have in my house. I've got, one zone for my whole house. You can get multiple zoning, which makes it A, more comfortable, B, you can set back the rooms that you're not using at the time. You've got a spare bedroom or whatever, you can set that one down at 60 and save more energy. So yeah, that's unfortunately the solution for those. And you do want to, and I don't know what the state's doing with the program yet on getting your house sealed, but hopefully sealing from infiltration is a big key to helping the heat pumps work efficiently.
Okay, I think we have time for one more, and then we're going to switch over to Alan, the second speaker. So Thor asks, I currently have hot water baseboard heat, which operates with water at about 160 degrees Fahrenheit. Is there a hot water heat pump system that can provide those temperatures to work with my existing baseboards?
This is a question I ask every day, and the answer so far is no, not yet. They are supposedly coming to market. It requires basically carbon dioxide as a refrigerant in a two-stage unit, but there's nothing on the market in the United States today. There was at one time, I did put one in, but they took it off the market because nobody was buying them. Well, nobody knew that they were available, so nobody was buying. So hopefully Mitsubishi will bring theirs back, or one of the other, I think, or maybe it was Daikin.
Bill, I will give you one more question, which I think is just a yes/no question.
Okay.
Does this energy information apply both to duct and mini split heat pump types?
It does, but not all are cold climate. Most you have to look, you have to make sure you're looking at the cold climate versions, not their standard versions.
Okay, thanks. There was a lot of information there, and we'll get to the rest of the questions after Alan's talk.
Okay,
So
great.
thanks a
Bill,
lot.
Bill, do me one favor. Put in your email address in the chat for the person you suggested get hold of you by email.
Okay. Yep.
Thank you. Our second speaker, Alan, wins my prize. He's been on the hook for the longest time. I've been continuously reeling him in for one full year. He first won a time in the April 21st, 2022 webinar. But I think you're going to agree that the wait's worth it because it was a unique project. He will discuss his design decisions for his all-electric, beautiful 4-story beach house. And I think you're going to agree it's really elegant. With that, go ahead, Alan.
Okay, you can hear me clearly, I presume,
Yes.
right? Okay,
Yes, we can.
thanks for having me on. And Bill, great job there. You know, I had to learn a lot in my process, and I'll discuss some of that as a homeowner, right? Which is very difficult because you're pulling together a lot of pieces to, let's see if I get the slideshow going. Okay, my name is Alan Porto, and why I was requested to present here, I wasn't sure really the best way to take this is because I'm trying to create an all-electric house. And you know, what is my background as a homeowner? And I'll just show you the picture because pictures, you know, help get individuals inspired about what the person's working toward. It's a beachfront house. It's very beautiful. It was designed by an architect by the name of Milello Architecture out of Brielle. We have not yet built, but there's been a lot of thought put into this. And how do you make this completely electric and go 100% off grid, right? And so just some of the thoughts in the house. It's in Seabright. It's going to be 4,300 square feet. We'll have a number of bedrooms in there. It'll be 3-car garage, right? And we'll have, you know, some of the things in terms of, you know, making it energy efficient. Certainly we'll have the 6-inch wide walls. We'll do some sprayed foam. We'll have potential windows in there to upgrade, and there's always, you know, what should you do? Should you do 3-pane or not? So some of those final considerations are not really done. Really, what was most important to me as I was going through this was not just, you know, how well it was insulated, but how do I get myself off grid? Now, this slide here shows a lot of technical information, some money that's associated with it, and I think this is important because, you know, people want to know, does it work and how much does it cost and what's my benefit? Why would I spend all this money to make my house go off grid? So I'm bringing these numbers to the front. Some of these data points are probably not things that you're as familiar with, but if you are going to go into this journey, you need to become somewhat more familiar with it. So what was my approach? I decided to go with a Tesla solar roof. The roof itself are solar tiles. They look like the bottom right here. And they produce enough electricity to support, the goal is to produce enough electricity to support the house. But that solar roof only produces so much that the house still needs to draw, in the evening, and it needs to be able to draw over periods of time when there's no sun, right? So you have to take all those points into consideration. And if you try to go all electric, you have to think about the conversion of traditional gas to BTUs to electric consumption. So it becomes very difficult. But I try to maximize what the roof would be capable of supporting. And I had to go through this conversation multiple times with Tesla, who designed it on the left side here, where you see those little white grids of where the tiles will be stored, right? These white grid tiles are actually the solar tiles on the roof. The total cost just to get to the punchline is $63,000, but after credits, it's $44,000. But along with those tiles are batteries that will store the solar energy for night. So along with the tiles, I'll get 4 Tesla batteries. On the right side, you'll see what the batteries look like. They're actually aesthetically beautiful. The tiles are integrated into the house. They don't look like, you can't really tell that they're solar tiles looking from the street. The benefit, if you have a home, and this is, everybody's different in how they consume electricity, but on average, on a 4,000 square foot home, you're probably spending about $3,000 a year in electricity. You're probably spending about $3,000 a year in gas, right? So that's $6,000 if you can get that fully off grid. Over 20 years, that's $120,000 savings without figuring out interest and your net present value calculations that go along with it. So even though it seems like a lot to spend for $44,000 to put in a roof and batteries, the savings is enormous. A traditional roof with a generator would cost about $35,000, is my estimate on a home like this. So my uptick is not that much. My savings is enormous over the long term. To give some additional specs on these, maybe I'll get into it a little bit later but this system works off your phone. So your cell phone has an app, and it runs between the roof and the battery. I'm a big proponent of the Tesla. I believe, as many of you are following Elon Musk nowadays, he truly has the best practice. Why is his technology superior to everyone else's? He has probably the biggest research and development group in technology in the world. It is a combination of not only his car company, but his solar company and his space company that also has satellites. And all those play into each other in terms of creating optimization in the development of batteries and efficiency of use for electrification. So my bet is with him, and I believe my benefits will continue throughout the house. As with your Tesla car, if anyone owns a Tesla car, they understand they continually get upgrades and benefits through the car after the purchase of the car. I presume I'll be getting these same benefits with my solar solution as well. Moving on. So what are the benefits of going with Tesla? The goal is to go off grid. I've explained to you the savings of money, right? The electric products are much quieter, right? People don't take that into consideration. They believe a lot of individuals may have generators on their house, which are gas powered most of the times, right? Very noisy, inefficient. My batteries will act as backups to the house when there's no solar light. There is a warranty on it for 10 years, and they guarantee it'll have 70% generation off those batteries. The roof is a combination of glass and metal, right? They put a 25-year warranty on it. It's wind rated for 124 on the internet, but internal documentation shows it's wind rated for 192. For me, that's important being on the beach, right? And I'm eliminating, carbon dioxide and other burning pollutants, right? In my home, from furnaces, fireplaces, your stove, hot water heaters, right? All that I'm trying to get rid of, right? So I'm trying to use electric cars. I already have 2 Teslas, right? Which is probably more than most, but most of you are looking at electric. If you're buying a new car, it's a consideration. Well, I'll be charging this for my house. I'm looking at using induction range ovens over electric. I'm trying to use a VRF HVAC, which Bill will understand what I'm saying when I use that word, right? Which is with hyperheat. I'm going with electric fireplaces. I'm looking at continuous hot water, electric dryers, and electric radiant floors, right? All of that electric, right? So what's the problem with that? Well, it's a lot of consumption, right? So what I've learned is each of the Tesla cars requires generally about 40 amps to charge. And if you're doing a level 2 charger with Tesla at home, if you're on E, it takes 6 hours. Say you have 2 cars, you're trying to charge from E, that would be 80 amps of trying to usage or balancing it. Induction range ovens can use 50 amps. Electric continuous hot water, 100 amps, right? And plus to start up anyway, right? And it's not running throughout the whole day, but at the time that you need it. So how do you balance all that out, right? Fireplaces can be 110 or 240, right? Radiant floors, electric radiant floors consume a lot of amperage, right? Your hyper heat pumps and the VRFs, electric coolants requires more. If you have a jacuzzi and a pool, right? All this keeps compounding. What about barbecues? People usually use gas, coal, but what about going electric? There's a lot of barbecues now that are kind of griddle, right? The griddle ones that are out there people like, but they're running them off of propane or gas. Why not use induction, right? So these things I'm trying to consider, right? And you only need the heat in the sun in the winter, and you need the AC in the summer. So maybe all this balances out. It's hard for me to tell. I did an energy consumption schedule, a very detailed one. It seems like I went off the charts, but it's very hard to kind of know exactly what you plan on using in a day. So what are some of the challenges with electrification? One is educating yourself. It's very difficult to educate yourself on this because every piece has a different consideration to it. What is the quality of the product? What does it really consume? There's very few people I found that I can confer with to discuss all these topics in one go, right? And there's a lot of opinion. I get a lot of individuals that will say they like a gas stove because they can see the flame. That's great, but is that really needed? And if they started with an induction range, which is different from an electric range, if you don't know the difference, an induction range uses off of magnetized pots and heats much quicker, right? So, learning this and then kind of getting through that and bringing everybody on the same page is difficult. Try to win over your family, your friends, the architects, engineers, the builders, the town, the utilities. And it becomes somewhat exasperating because not everyone is trying to go fully electric in a house. I found that, maybe it's building up, but it's still an evolution at this point. And then just educating others. The hard issues were aesthetics, performance, and cost, right? What are the things that work? Which ones do you trust? Where do you put your money to make sure what you're doing is a good decision? The geothermal is an awesome conversation as well, which I was looking at over the traditional VRFs, which are over, right, the traditional HVAC that you have in your house. My concern ran into using it in by the ocean and the water, and really having people that know what they're talking about to put these things in, which is very difficult to find. Determining your actual usage or discuss that. What is the production? One of the issues I ran into with Tesla is that they started off with a 9.2 kilowatt production for me. I pushed on them. They gave me 9.7. The person left the company and I pushed again, and now I got 10.7. That just came through today, right? And I've been working with Tesla for almost a year on their design. So it's interesting that you got to keep going back to sometimes get what you want as much as you can, because I wanted to maximize the production of my roof. And let me just come back to the screen. These are things to consider, like we're going with the Tesla tiles. The white is with the solar, correct? But the black doesn't have solar, right? All these areas. Now, there's certain amounts they're willing to fill, maybe some restrictions, maybe it's too small, but even here, I have a question. Why would they not fill this up and give me more solar production during the day? So to continue, selecting the right equipment, communications, installation, support. I've learned that lighting rods are not supported with a Tesla roof. Controlling my costs overall has been a concern because, everyone has different price points of what they would charge for doing some of the work, right? And just talking to my builders, a lot of the builders, they don't converse. My architect didn't want to work on the HVAC as part of the work. I go to the builder, they're like, well, we usually work with it and don't deal with the architect until we build the house, and then it's site on spec. with installation, which is another problem with the HVAC. So I was trying to work with a number of people to design it ahead of time so that I knew what exactly I'm getting. And so a lot of the units that Bill was showing there, I've already studied as part of the house, whether I'm using cassettes or mini splits or various types of internal HVAC usage parts. And so with that, that's my presentation. I'll be happy to answer any questions from here.
That's great. Thank you, Alan. We actually have only a couple of questions for you so far, but people, since you're done, people might be putting more questions in. But the first one is, now where did it go? The first one for Alan is, what are your plans for resilience given the projections for sea level rise over the next few decades, and given that you're building a house at sea level?
And is it resilience for electrification or resilience just in general for the home? Right. So, and maybe I'll answer maybe a little bit of both ways. Right. So resilience on the home, certainly we're between the floors, I'm putting in 16-inch trusses rather than a 12-inch joist. And those create a lot more structural integrity of the house. But from an electrification, the Tesla roof, one of the things I mentioned earlier is wind rated internal documentation for 192, which is enormous capability, at least for the roof. I've also worked with a geotech engineer on studying the ground and the soil to ensure that we have strong stability. And we actually moved away from using pilings to a spread footing. So we have a pretty impervious spread footing design for the house.
So, Alan, this is Marty. I'm the one who asked that question. And I guess if we thinking about something like Hurricane Sandy that happened, just a little over 10 years ago now, how would the house survive an experience like that? I guess, and perhaps a storm surge of several feet of water coming through.
Well, that's a great question, and it concerns my wife too. She always brings it up as a reminder. First, I guess a couple, for me, we have a wall in front of us in Seabright. So if you know the Seabright location, there's a 12-foot or 15-foot wall that I think helps protect us. So that for me, I have less of a concern. But Sandy was not a wind issue, I understood. I believe Sandy was that the water rose, right, and then pulled everything out. So there is a concern, but again, I had a geotech look. We're doing some very large spread footings, and then there's structural integration between the design of the house so that everything's structurally integrated. So the whole house would have to be moved, but it would be moved in one piece. So it had to take a lot to move the house, but anything's possible. But they don't see an issue with the Sandy ordeal causing an issue with the home or where I placed it. So that's the best I can answer it. But yes, it's always a risk. I think when you look at homes, everything does matter, right? From, the foundation of how you design it to the structural holding of it together, to the roofing, to the window integration, right? All pieces have to be looked at. And we've went through countless iterations of looking through the things to see if we can tighten it up more so. Nothing is perfect, right? We didn't go with hurricane windows. Very expensive. Concerns with firemen getting into homes, right? If you study that. Also not perfect if you have something coming in as a straight through break, into the window. So we decided at the moment not to go with the hurricane structured windows. That's probably the one upgrade we can consider that would make it more impervious.
So are you completely off the grid, or you're connected to the?
Well, we haven't built yet, right? So
I understand. In terms of your planning.
Yeah, the planning, it's a question because I can't really get clear answers. My design shows, I believe I can be off grid. I believe, look, if everything is being used at the same time, I don't think it'll support it. One of the things I didn't mention is that, you have to make sure the utility provider can give you the amperage, right? So I think I'm going to get 400 amps to the house. So That's not meaning off grid, but if I need to use the utility provider, I need to be able to consume, right? If I have 2 or 3 or 4 electric cars at the house, because I'm assuming in 10 years, everyone's driving electric and they're coming over to charge, right? For whatever reason, I need to be able to support all that. So we'll have a 400 amp line coming in. We got lucky. I think it'll support it without any cost to us. And we believe I'll be mostly off grid. And if I go back to the numbers that I mentioned earlier, I'll have 10.7 kilowatts produced from the roof. I have 4 batteries that are 13.5 kilowatts apiece, right? So the question is, how much storage will I be able to create and how much consumption will I need at any given time, right? And that's kind of the balance, right? With the Tesla app, I understand I'll be able to balance things out if I need to with consumption of less items if I want to kind of take them off usage. But we'll have to monitor it. That's the best I can say. And I think we'll be fine. The other thing I want to say is that my current house consumes, and it's, if you look at homes that are about 3,500 square feet, they consume probably about 10 kilowatts a year, right? I think that's probably a fair number, right? So remember, I got a 10 kilowatt production solar roof, but I also have 40 plus kilowatts of battery storage. So I think the combination of the gas BTU plus the electric consumption on a very sealed home, right, should work much better than on a legacy home that's producing that much or consuming that much.
Are the
Let's,
batteries, are we
Marty,
let somebody else
Marty,
turn? Sure.
Marty, let's go on to the next person.
Okay, fair enough. Thank you.
We need to
Thank you,
give
Pat.
somebody else a
Absolutely.
chance. Thanks. You can come back later if we run out of questions. The next one is from Reverend Dr. Sandy. I'm not sure either Alan or Bill is directly related to this question, but I'll ask you either one, whether you have an opinion or not. We're planning to build a green, off-grid, intentional community for elders. Can you explain the difference between a solar farm and individual rooftop solar for 32 homes? What is better, dollars versus energy?
You know what, Bill, I'll give my first perspective on it because of my close understanding of Tesla, and you can jump in if, giving maybe your views. I'm sure everybody's got a different perspective. Look, certainly I haven't studied that, but I would think just at a perspective level, it's probably easier to build a solar farm, right? Because they're just panels that you're putting, on a piece of land, right? If you have a large piece of land, but aesthetically, I'm going to say 2 things on the solar roof that I think are very important that people tend to forget. One, aesthetically looks beautiful. It's right on your roof. The test, not solar panels, but solar tile roof. The second thing is it is wind rated and hail rated to take a hard hit, which is much better. It'll last much longer than your traditional roof. The third thing that most don't realize is that most roofs are asphalt. So by going with glass metal, you're going with a much more environmentally sound solution rather than asphalt that breaks apart over time and draining into the sewer and water system, right? So there's other benefits to it that I think you'll get. I don't know if the total, if you have just peaks on your roof, that's your best design for collecting and maximizing the use of solar tiles on the roof. If you have a lot of changes, you're going to get less, and maybe the farm becomes a better solution.
Okay, thanks.
Yeah, so there's really some significant differences. And one of the big issues you'd have to address is who, for 32 homes, does each home have its own meter? Or are these kind of all on one meter? Because that would make a huge difference. If each home is as they would normally have their own meter, then putting the panels on the roof would make a lot of sense because it's going directly to that individual user. When you do a community solar, the economics change because you're not any excess power, you're not selling back at a retail rate onto the grid. you're connecting you're ahead of the meter instead of behind the meter. And so all the financial rules with the utilities flip-flop. So it's something that there's a lot of questions you have to answer to get a good answer to that.
Yeah, sounds like a big project that does have a lot of questions to answer.
Yeah.
A simpler
Sounds like a great
thing,
project, though.
this is for Alan. Sue wants to know, was there much pushback by the local town government?
No, actually, none, but we came in with a planner, an engineer, an architect, and one other person I can't remember right now, to the town meeting, and we answered all questions for them, and it went very well. But we came very prepared with a lot of documentation. So no, there wasn't any pushback from the town.
Kathleen asked, where are the utilities located? It seems like the utilities are going to be only electricity, and well, I guess you have sewer and water.
So from a
that's
location,
question.
well, first, the utility line, I will have a utility line still running to the house as a failover, correct? The goal is not to leverage the utility at all. We might have to at some point, but we don't believe we will. So what happens is Tesla's system automatically goes to the utility should it not have enough capacity for the house, and we'll draw from that utility. The utilities will get located just like you would do it on a home. Would come in down, you'd have a box on the outside as a meter, but then they have something called an inverter, and that inverter works between the Tesla solar roof, I guess the battery, and the power company to determine when it needs to draw upon which. If it needs to draw upon the utility company, it would decide to do that. The system would make that decision.
Okay, thanks. I think we're at the end of the questions specifically for Alan. So Marty, if you have another question, you can ask him, and then we'll go back to the ones for, and I think Alan needs to run. So when you have to leave, Alan, you
I will do it. Thank you.
can just leave.
Thanks, Pat. I think we ought to just move on to the other questions. I appreciate the opportunity. And Alan, thank you very much. Looks like a very exciting project that you have planned. I really wish you a lot of success with it.
Thank you for that.
Okay, thanks a lot. I'll circle back around. We got almost to the end of the questions for Bill. Let's see. Okay, Linda wants to know, are there any certifications I should be looking for when trying to find a contractor?
I wish there were. I'm in the business, and I've had a hard time doing this myself. I had to get a contractor to, and although they sounded like they knew what they were talking about, this is the first time they ever installed this type of unit. I did help my son convert his house. So if you can, the various manufacturers, Mitsubishi, Daikin, LG, they qualify their installing contractors and some will be like a gold level dealer for that particular brand. So you'd have to like reach out to contractors in your area, use Google to see cold climate heat pumps. They're unfortunately few and far between at this point that really have experience with this because market hasn't demanded it. Once market demands it, they'll learn it, but nobody's really forced them into that yet. So that's why this part of the process that the state BPU and DEP are working on one of these things is contractor training, to get them up to speed on these new units. They're not really different to install. They're just a little different to start up. So it shouldn't be all that difficult for them.
Okay, thanks. I'm not sure I can read the name of the next person, but that person says, in a condo, I have a gas furnace replaced 10 years ago and same aged air conditioner. How do I know when to replace these?
So again, it's kind of like, what's your motivation to replace them? Are you just looking at the economics, or do you want to decarbonize your footprint? After 10 years, they've probably got a 15-year life. So it's not unreasonable. And the energy efficiency improvement from a 10-year-old unit to a current unit is probably enough to get you a rebate from your utility. So that makes that decision somewhat easier. Also have to look at, it's depending on the arrangement of the house, the size of the system you have. Sometimes you can just do a 1-for-1 replacement. Take the furnace out, put the heat pump in. But in some cases, like my son's house, we did that, but that only gave us half the heat we needed for the house. So we had to install another unit on the second floor. Another version is a hybrid. One of our engineers here just did that at his house. He's up in the woods. He's got oil heat. He replaced his air conditioner with a heat pump. The heat pump does his heating from 60 degrees down to 35 degrees. Below 35 degrees, his oil furnace kicks in. So it's not carbon free, but he's reducing his oil use very dramatic. And that's an economical solution. So
I'll just add to that is an easy thing to do. We just did that. We replaced the air conditioner, but we left the furnace, the gas furnace, where it was, and are using that as backup.
Yeah.
But we use very, very little of it. Our gas bill is close to nothing now.
right. That's a very good solution.
Okay, here, I'm not sure exactly what this question is, but do any of the systems that you talked about, Bill, have SEER ratings that meet JCP&L rebate standards?
Yes, they certainly do. Most of the units I'm talking about here will qualify for rebates from JCP&L, PSE&G, Atlantic City Electric.
Okay, thank you. Now I'm going back down to the bottom. Okay. Question is, I would like to hear more about heat pump hot water heaters. Oh, hot water heaters.
I sort of answered that. If there's a lot of material in the reference that I cite in chat, if you'll see the last entry, just click on that URL and you'll find about 300 references, and they're sectionalized. So look at the section talking about heat pump water heaters. And there's one in particular I'm thinking of. It's a direct comparison of current and some brand new versions of hot water heat pump water heaters that's very educational.
Okay. I'll just to follow up, I think, for Alan. Kathleen says, she's the one that asked the question about where the utilities are. She said, I meant the batteries, not the HVAC units. So where are the batteries?
Well, so there are 4 batteries. 3 of them I sure will be in the garage, an interior wall. The fourth one will probably be in the garage, but I might put it actually outside. And the reason why I brought them into the garage as much as possible is because of the salt water. I want to keep things away. Although the batteries are fine to put out in the outside, I just think it would be better to store inside. So they're in the garage at the moment.
I think we've just about gotten to the end of the questions, unless I missed something. Does anyone else have a question that they want to ask before we close?
And I have the question I didn't ask before. Are the batteries watertight if there's flooding? Are they protected against water, and also the connections that connect them to one another?
Well, I have to be above the flood zone, but I understand from Tesla that I think it's up to 2/3 of the battery. Let's just say half of the battery can be submerged below water.
Okay.
Right now, they could be outdoors for rain, but
Mhm.
submerging them, I
Right,
think at
right.
least half. I think it was 2/3 though can be submerged.
Okay, great. I'm learning a lot. Thanks for sharing all this information.
Yes, thank you both. This was really very, very informative. Steve looks like he wants to say something.
Yeah, I really appreciate both of you for talking to us tonight, and tomorrow or so we'll send out the recording and the slides. I wanted to put a plug in for our next webinar. It's going to be Thursday, May 18th at 7 p.m. And Pat and I are going to be featured because as of midnight tonight, my wife and I have concluded 2 weeks worth of Climate Realty Power Up training, along with Kathleen, and maybe others on this conference as well. And we're incorporating the last 2 weeks of material. It's the latest Al Gore's slides, and they're really, really good. That incorporates stuff about what can we gain from the IRA and the Inflation Reduction Act and the Infrastructure Act. So we're going to send out an announcement. Sorry.
We also want to talk a little bit about the material that we gave to Sierra Club, and tell everyone how much money we're saving with our first year of the heat pump, which is 20%. So we want to sell heat pumps to everybody.
Yeah. So we'll cite ourselves and also cite numerous examples, summarize it, but numerous examples of people going toward net zero, and there's a lot of people. So that's all on our next program on Thursday, May 18th, 7 p.m. We'll get an announcement out later. So thank you all for joining us tonight. It was great. I'm glad that Ellen finally was on our show. Thank you, Ellen. It's been one full year.
Yeah, that was
And Bill,
fascinating.
thank you. You're a wealth of expertise.
Thank you. Thanks
Our
for having
pleasure.
us on.
My pleasure. Yep.
See you all in a month.
Okay, thanks.